Okay, Adi.
Hi, good morning, good afternoon, good evening, everyone. Welcome to the Geoscience and Geoenergy webinar of today, 17th of June 2021. Today, Sebastian and I are delighted and pleased to host our colleague Aaron Cahill from Herriot University. Aaron is assistant professor at Lyell Flow in applied geoscience at Herriot University as part of both the Lyell Center and the Institute of Geoenergy Engineering. So Sebastian and him should be very close colleagues, I guess. Aaron's research concerns the environmental impacts of geoenergy techniques, including geologic carbon sequestration and unconventional gas development, with a specific expertise on well integrity failure, subsurface fugitive gas migration, environmental fate, and impacts also. A hydrogeologist by training, Aaron received his undergrad and graduate degrees both from the University of Birmingham in UK before working in industry for several years. Subsequently, he attained his PhD in environmental engineering from the Technical University of Denmark, undertook a 3-year postdoctoral fellowship at the University of Guelph in Canada before founding and serving as the director of the Energy and Environment Research Initiative at the University of British Columbia in Canada. So starting in UK, Denmark, Canada, so he has not stayed in one location, I guess, for that long time. So it's very mobile and dynamic career.
Too much, Adi, too much.
Aaron has published more than 25 scientific articles and technical reports on various aspects of geoenergy and potential environmental impacts. In addition, he has 9 years of experience leading the establishment of and managing research at geoenergy-focused field research stations. It's our honor and pleasure, Aaron, to have you and host you here this week. Thank you for graciously accepting our invitation. To the audience, please note his lecture would last for about half an hour, 35 minutes or so, and then, like always, followed by discussions and questions. Sebastian will take care of the discussion session as always. And please be reminded that type in your questions whenever appropriate. Your question may trigger other colleagues' questions too. So do not wait until the end of the talk. Post your questions, and we will host also a lively discussion session on this extremely important and timely topic on legacy wells and their integrity. Thanks a lot, Aaron, for your lecture in advance. We are all looking forward to hearing your talk.
Thank you very much, Hadi and Sebastian, for inviting me. It's an honor to come and present today, and thanks for the really generous introduction. So as you say, I'm going to be talking today about legacy wells and their integrity, with a lot of descriptions of some really field-focused research, mostly field-focused research, which I've been involved with in the last years, and really coming at that from the angle of thinking about net zero and how legacy wells and their integrity need to figure into that, because we really need to consider that as we move into the future. So on that note, obviously working towards net zero, this is what many people are focusing on these days. If I needed to explain this to my 4-year-old son, the easiest way is, of course, in the past, we've looked a bit like this picture here, where we've perhaps been unsustainable, and some of particularly our energy resources have been net positive in terms of carbon and environmental impacts. And we want to move towards this green, more sustainable future where we're in a net zero situation, particularly in terms of carbon. And how we're going to get there, we're all working very hard on trying to achieve that. However, we have to still consider our net positive past. Of course, the last 150 years or so, the majority of our energy resources have been attained from petroleum resources. And during that period, you can see here this map from IHS Markit, We can see drilling density across the world, some very dark shaded reds in North America through the Middle East, all the way into the Asia Pacific region. There's been about 8 million, more than 8 million petroleum wells drilled since we've been using these resources for energy. And eventually, and we're already working on this, of course, globally, all of these wells will be sealed, decommissioned, and hopefully in perpetuity. We want to seal these up and have them completely decommissioned and look towards this net zero future, which is a huge ongoing job, with the majority of that to be done into the future. So nothing to worry about, right? We're just going to pack up and seal everything as best we can, and off we go into this new net zero world. And here we see a nice historic picture from about, I think this is about 120 years old. This is McClintock Well number 1, which is apparently the world's oldest continuously producing well in Pennsylvania in the US. And presumably this was plugged up, and all the other 8 million are going to be plugged, decommissioned, and we're not going to have any problems. Well, unfortunately, that's likely not to be the case. So one thing that industry and all various stakeholders in petroleum resource development have been grappling with and dealing with for quite some time is general well integrity. This is always a challenge. It can be a challenge in certain areas for lots of different complex reasons, and well integrity can fail. So we have these issues with petroleum wells in certain situations where we get integrity failure. And there's many different points and parts of a petroleum well where this could happen. We look at the different structure, the different cement sheaths, the casings, the plugs. We've got different parts can fail for different reasons. And what this ends up with is we get this undesired movement of petroleum fluids, typically buoyant natural gas, moving around within and outside of the structure of the wellbore. And in this case, we have what we call inside casing flow, or gas migration outside the casing. You can see on the right-hand figure here with the blue arrows where gas actually moves outside of the well structure, or the red arrows where it stays inside. But nonetheless, it's moving where we don't want it to go. So this issue of well integrity is, as I say, is not really a new challenge. And it's an area of historic and ongoing concern for all stakeholders in petroleum resource development. And to demonstrate that point, there was some very nice work done in the 90s. This is something which really isn't a big surprise to industry, and they've been trying to get this sorted out where they have these more rare occasions of this. And pretty much it is accepted that there is a number, and inverted commas there, of energy wells which do exhibit this integrity failure. And when this happens, we get this either inside casing, fluid movement, and gas often can reach then the surface and emit as a greenhouse gas into the atmosphere, or sometimes when it leaves the structure of the well, it then travels off into the subsurface according to the laws of multi-phase flow physics, and we can get issues like groundwater impacts. And there's multiple documented cases of this in various areas to different extents, but it's definitely not really a new issue, and not necessarily super common, but it's also not necessarily rare either. So just to rather than show pictures and talk about it, here's a little video of exactly what happens when you have integrity failure. Let's just go back here and click on this. You can see here, this is a well with integrity failure. So hopefully you can see this nice jacuzzi of bubbles around the casing. And maybe you can even hear that as well, this nice bubbling sound. And of course, this is not supposed to happen. Nobody wants this to happen, but unfortunately, in this case, it's happened. So this is exactly the result of integrity failure. And you can imagine this gas here is emitting straight out into the atmosphere. Okay, so should we be concerned about this issue? Well, of course, I'm arguing here that I think we should at least be thinking about this and a little bit concerned. You can see here a graph from Nature, a recent article in Nature Online, and we can see here that every year we are reaching record highs of atmospheric levels of methane. And you can see here since the 80s, as we move through into 2020, there's actually even quite a an increase in the rate of increase of methane in the atmosphere, and this has been pretty much attributed, at least in large part, to the increase in natural gas development since the early 2000s with the advent of hydraulic fracturing and horizontal drilling. And of course, this is a big concern as we start to think that every well where there's an integrity failure, we have these methane emissions either into the environment, which may or may not reach the atmosphere or impact groundwater. And each kilogram of methane that's released is equivalent to approximately 84 kilograms of CO2 over a 20-year period. So you can see there's quite a powerful warming effect of this gas. And we can see these increases. It's been shown quite comprehensively now that there is this continuing increase. And one of the biggest issues, and something I'm particularly interested in, is that this incidence of failure is how many wells fail, basically. It's very uncertain and poorly constrained. But if anything, we have to assume as wells structures age, there's going to be an increase in the number what do fail. So there's definitely a need for management and mitigation of this as we move into a net zero future. So what I want to talk about today on this topic is I want to use a bit of a case study of a region close to my heart where I worked for some years, which is the Western Canada Sedimentary Basin. So over up in Canada, we've got this huge sedimentary basin, very famous for energy resources. And if you look at the statistics there, we can see there's been more than 500,000 oil and gas wells have been drilled across that basin. And in particular, in the last 20 years, this has been a region which has seen a huge increase in the amount of unconventional resources which have been developed. And in fact, you can imagine with so many wells being drilled, there's just increases the chances that you could have issues with various wells and different failures of integrity. And integrity failure is an ongoing and growing concern in the area in general. And people are thinking about this and looking very proactively at managing this issue and trying to understand it as best they can. And it's something there in Canada, in Alberta and British Columbia, which is quite often in the news and in the media as big election issues, as people start to look at particularly what happens when all of these wells are decommissioned in the future. 500,000 of them still existing. Although plugged, they'll still be there. And there's starting to be some concern and planning and strategizing between what should be done to really look after this properly and make sure it doesn't cause an issue into the future. So zooming in even further, so where I'm going to be talking about some of the work I've been involved in today is in northeast British Columbia. So it's the top little corner of the Western Canada Sedimentary Basin. And it's in some ways a bit of a smaller region of development compared to its neighbor, Alberta, next door. There's about 25,000 energy wells drilled there. There's been a huge amount drilled since the 2000s, with several big unconventional resource plays there. For example, the Montney Shale is in this region. So there's been a huge amount of additional drilling since the 2000s. And if we think about well integrity failure, and we look at the regulatory records, and a lot of this work has been done in conjunction with the regulator, we see that there's been sort of close to 3,000 cases where we get inside casing failure and gas is moving around inside the casing, and about 145 outside the casing where gas has been detected around the well bores there. And we can look then at a map of this in terms of where the leaking wells are, and we can see sort of a spread across the region. Here you can see on the map where the shading shows how many wells there are per 25 kilometers. You can see a bit of a group, a cluster of gas migration wells up in the sort of northern portion near Fort Nelson. And the regulator themselves have looked at this and have been thinking about this, and do accept that most likely this number of cases that we have documented is probably conservative, as field screening methods don't always catch everything, and certainly all the other wells haven't been tested negative. It's more the ones which have been reported where you have a positive case of integrity failure. And just to put this in context, you can see, as I said, next door in Alberta, there's a lot more wells. We get a lot more cases of integrity failure, but it is a real issue to have to think about and manage, and that's what we've been trying to do. So part of the research, or most of the research I'm going to describe today, has been undertaken as part of the Energy and Environment Research Initiative. So this has been a really productive research group, which I've been proud and privileged to be a part of, with lots of great colleagues in the last years, and I'm still involved from my new position in Herriot University, and we're still working up on a lot of these issues. And it's a real field-focused program. We've really been out in the field looking at what's going on, trying to understand the real world situation, and lots of sponsors, lots of partners in this, and I'll acknowledge everybody at the end. So just to give kind of an overview of boiling it down to the three key questions which in ERIE we've been trying to address. So with respect to well integrity failure and the region of British Columbia. So the first one is, why do wells fail? Why does well integrity fail? Obviously, if we can understand that, we can start to think about if we can mitigate that and prevent the problem before it even happens. How many and where do wells suffer integrity failure? So how big a problem is this? Often there can be knee-jerk reactions that is happening everywhere all the time, or conversely, you get the opposite suggestion that it never happens. And of course, neither is true. Often it's a sliding scale, but can we characterize and constrain that? And then finally, how bad is failure? If there's a failure in a given area, how worried should we be? How bigger impact does one leaking well or multiple leaking wells have on the environment? And so these were the key questions we're really trying to address here. And I would argue these are going to be pretty essential to address as we thrust into net zero, and we really want to truly reach a net zero status. So firstly, why do wells leak? So a short while ago, some colleagues and I, we got a research project underway in collaboration with the regulator in British Columbia. And very fortunately in British Columbia, they keep very good records of that oil and gas development. And this also likely is a result that a huge amount of the development has been since the early 2000s. And since then, it's much more easy to keep very good electronic records and so on. If you compare that to somewhere like the UK, in England, for example, we have some onshore wells drilled since 1903, and you can imagine records weren't perhaps kept as well then. But in BC, they have very good records of lots of different aspects of all the energy wells, all of their construction details, all of the geology details, and so on. And so what we wanted to do in this project was look at what characteristics of wells might be associated with integrity failure. So is there some commonality between the wells which have leakage, have integrity failure, and which differentiates them from those which don't? And the goal here was, if we could find out any factors which would increase the risk of failure, we could then bring that into helping with detection efforts and risk management approaches for industry and regulators. And it's resulted in a nice little recent article earlier this year. So the regulatory database interrogation exercise. So we looked at various attributes of each and every single well in BC. We looked at things like completion details, the depth, orientation, if they had any treatments, for example, hydraulic fracturing treatments, surface casing depths, so on and so forth, drilling methodologies, whether there was kicks or blowouts, and also looking at things like the subsurface environment in which the wells were hosted. So for example, how many wells were nearby, what type of geology was intersected. And what we did, we had a very excellent student named Elise. You can see a picture of there. She did an absolutely excellent job of deploying some good statistical analysis on this large data set. So she took a contemporary approach using some Bayesian inference and hierarchical model structures to look at basically multi-level logistic regression models. And she took the 23,000 wells in the whole of BC, and also focusing in on that little clustered area, which you could see in the previous map. And she got a model set up and looked at the different variables and trained the model with the well data, and then looked at the results. And from then we were able to then start looking at what of these factors was typical or a commonality of wells which suffered gas migration. So we can see here the model coefficient results. And so without getting into the weeds of all the maths, basically this is the key part of the statistics, where we see which factors which we include in the model either increase or decrease the probability that gas migration would occur. And what we found here was these factors here, so whether or not wells had additional remedial treatments, or if there had been blowouts during drilling, and whether there was inside casing flow, and or whether or not they intersected an overpressurized gas-bearing formation, seemed to increase the probability, while these factors below seemed to decrease the probability of gas migration. So this was interesting. This started to give us some idea of what might be a causal factor with relation to integrity failure. So overall, I think one of the powerful kind of sentence which we had in this paper here was that, interestingly, and this was actually one of the key things we were looking at, was whether or not hydraulic fracturing seemed to play a part, which is definitely a concept or a theory posited by many, and sometimes often held by the general public, that fracking inherently causes more issues. But what we found in this statistical analysis is there didn't seem to be an association statistically between whether there was integrity failure and gas migration and hydraulic fracturing. In fact, nothing really strongly seemed to be linked to whether or not gas migration occurred. So there was no overall well construction or operation attribute what conclusively led to gas migration, which was in a way a good result. It shows that overall we are not doing anything wrong in a blanket way. That being said, there were variables which had the strongest relationship to failure, which included other indicators of failure and spatial and geographic location. So this started to point out that once a problem well, often it carries on being a problem well. And if you keep trying to fix it, it's difficult to fix. And also some regions just seem to have more issues than others. So this kind of spatial geographic phenomenon. So overall, what we saw here then was that integrity failure is actually very nuanced. It's complex and multifaceted. You know, we're not coming out with one simple answer of why it happens. There's obviously a complex combination of factors which have to compound to have this actually take place. There was a lack of data being perfect. It was a big challenge with this. So one thing to point out is, even though, and I mentioned this before, even though some wells have been reported as having failure to the regulatory authorities, the vast majority which have not been tested and proven negative. So there is some issues with that, and also off-balance data. The fact that you've only got 145 with failure compared to, you know, the other 22,850 odd which don't, and that's a bit of an unbalanced. And we're playing around a bit with that now as well to try and reduce the impacts of that. So definitely some limitations, but at least for now we have some ideas on what might be causing this, and there's certainly more work to be done on that. Okay, so next question then. So how many and where do wells suffer failure? So this is a big question. How big an issue is this in this region in particular? So first thing to point out is there's, of course, many methods to investigate this, and they have varying configurations and scales. And through our work with the Energy and Environment Research Initiative, we've been involved at looking at varying scales. You can look around known integrity failures, as I showed on the map there. It's a bit more difficult to do for sure, and we haven't been able to do that as much as we'd like with safety issues and proprietary data and so on with industry. There's ways to look more locally, but one of the ways most commonly deployed and has been deployed in other regions of extensive oil and gas development to look for impacts or signs of failure is what we call regional environmental forensics. So that's going very regionally and almost starting at the potential receptors and which are in and amongst the oil and gas wells, and almost sniffing around and seeing if you can see signs of integrity failure. So there's been controversy with this type of study in the past. However, they are very powerful as they give you the best idea of any impacts to receptors in an area, and in some ways are very essential and almost a given and a needed for public assurance, and regulators like to get this finger on the pulse. I mentioned some of the controversy with these. So back in the early 2010s, so about 10, 11 years ago, some of the first research of this style had some quite contradictory results, and we saw papers from looking in Pennsylvania, for example, where we had reports that there was links between distance to gas wells and concentrations of methane in groundwater, and there were other studies in the similar regions or very close by which found that was not necessarily the case, and actually it was natural factors such as topography which seem to control concentrations of methane. And this is just two examples, but there's been backs and forths and contradictions and different conflicting results on this, and not really getting full agreement or concurrence in the literature yet. So what about in BC? So this was one of the key questions we had for our region there. as it hadn't been done before, to look in and amongst that development, particularly in groundwater. And we got the opportunity to install a purpose-built monitoring well network in and amongst this extensive development in the Peace region of northeast British Columbia, up where the Montney resource play is. And you can see here, this map with the shaded regions is the energy well density. And you see the stars there labeled Erie. They are the purpose-built boreholes that we drilled. We drilled 29 boreholes, anywhere from 30 to 140 meters deep in and amongst this development, sometimes getting as close as 70 meters to an energy well, to look at whether or not we were seeing any signs of integrity failure. We coupled this with domestic well sampling. So this is typically what's more often done, where we just sample local people's wells, which aren't perhaps in the exact place you'd want. But we managed to get 427 samples from quite a few wells over about 5 years. And this was a huge endeavor. So lots of long field days, lots of drilling. You can imagine drilling 29 boreholes and all the sampling. And so yeah, lots of gratuitous field shots here. So what did we see? Well, we saw a very heterogeneous region in this area of northeast British Columbia in terms of the superficial quaternary geology. And so you can see here in this figure, which shows the geology encountered and the depth to groundwater, shows where we screened the monitoring wells that we put in, all 29 wells. And you can see here we've got this mishmash of glycogenic materials, often this veneer of till, diamictic till clay at surface, which overlies often some shale or siltstone bedrocks and sandstones. So highly heterogeneous, and we found varying amounts and qualities of groundwater throughout the region, and also found a few interesting and almost exciting, but not too worrying, artesian wells. You can see here one of the artesian wells here where the water was free flowing out of the well, which we were able to put a fit for purpose packer in there to stop that, and you didn't have to pump that to sample. So this highly heterogeneous region, so what we wanted to look at was dissolved methane in the groundwater, as is typically done in these style of studies. And what we saw here was, when we looked at methane concentrations dissolved in the groundwater, if we thought about proximity to oil and gas wells here on the left, or density of oil and gas wells, we wanted to take a look as this kind of quick first pass pulse check, and we saw really very little correlation between these two factors. So it didn't seem to matter how close you were to an oil and gas well or how many were in the immediate vicinity on what your methane concentrations were. And in that case, we conclude there's not really a link that's been seen in other places, and so of course this then doesn't seem to indicate there is a big widespread issue with integrity failure. So overall, if we look then at methane concentrations and plot that against the stable carbon isotopes, we see here this figure, this big shotgun spread here across the way. And really what this shows is there's no, again, signs of this pervasive impacts, which are sometimes feared to occur. So there isn't this widespread thermogenic gas leakage. So we would expect to see samples falling up in the red B region there if they have a gas which is more thermogenic, likely to be thermogenic from originating from oil and gas wells. Instead, we see the vast majority of the samples falling into the other regions, which are more likely to be either natural, we're getting their natural signs of degradation, and so on and so forth. And so in this case, we did have one well and one location where we saw signs which fell in this region, which we might link to energy well integrity failure. So in that case, while there's no pervasive impacts, of course, it is possible that you're going to get discrete events which may occur. And we're going to be following up to see what really is going on at this site shortly. Okay, so final question to answer then was, well, how bad is integrity failure? And if we think about a conceptual model of what happens when we get integrity failure at an energy well, we have some failure at some point in the well structure. Let's say it happens down there below the surface casing. We get a free phase gas leaving the well structure and migrating into the intersected geology as a free phase. Some of that will dissolve and then be able to move in groundwater if it's present advectively. And then there could be some reactive transport there as well with oxidation reactions. Some gas will stay free phase, and due to it, the buoyancy forces will push its way up like a bubble. You imagine coming up through the stratigraphy there, driven by multi-phase flow. It can reach then and go into the unsaturated zone at the very near surface to the ground surface. And again, we get different flow processes and perhaps reactions. And eventually it could emit to the atmosphere as a greenhouse gas and contribute to global warming. So you can imagine this is quite a multidisciplinary and interdisciplinary phenomenon. And really, we need to be looking at all different aspects of this process from the source of the leakage, from the wellbore engineering and the petroleum engineering, right the way through for the saturated zone, unsaturated zone, and then even having to consider meteorological factors which influence how the gas moves and where it ends up. And of course, there are many questions at all points in this, and so we've been trying there to elucidate and get a better idea of what happens at each of these processes, so we can better predict the migration, the impacts, and the fate of leaking gas to say how bad it actually could be. So, as I mentioned, it's very difficult to get the chance to study real leaky wells. It's for various reasons. So what my colleagues and I have figured out in the last years is that another way to try to understand subsurface fugitive gas migration is through controlled release experiments. These seem to offer a good way to look at the reactive transport processes where you have some control over the leakage rate and location, and so you can really look then. And we started over in Ontario, actually over in the east of Canada first, where we did a controlled release experiment in what essentially was a big shallow sandbox system in Base Borden, Ontario. And this gave us lots of really nice information. But what we quickly realized was we needed to be in a area more relevant to oil and gas development. There's not really any development there in this region in Ontario. So we there decided to do a controlled release experiment in Western Canada, in the Western Canada Sedimentary Basin. And we set up a field research station in the Montney resource play in British Columbia, where we'd be able to study fugitive gas migration in this very relevant geologic setting. And as I showed you before, this very heterogeneous glaciogenic geology there, and see how gas might move there. And we can see here, we're really in and amongst, on this map, we're in amongst this development right near lots of energy wells, including one not too far away where there is integrity issues. So a very, very relevant geologic setting. So the unsaturated zone field station, we set up an experiment in dry soils. So here we injected methane about 12 meters into the ground, and you can see this extensive monitoring network we have around this to try and track where the gas goes and what controls that. We saw some really interesting results here. So after injecting about 7 cubic meters a day for 5 days, we then monitored and watched the gas come up through the soils and how much left the soils into the atmosphere. And you can see this graph here shows the flux from ground surface into the air with the black dots there. There's the methane fluxes, and you can see these kind of sporadic burps of methane coming out of the ground. And the gray time series above that shows you the varying barometric pressure during that time. And you can see, of course, very clearly the barometric pressure seems to be very strongly controlling what comes out of the ground and when. And when we get these falls in barometric pressure, like this cascading series of drops in pressure, we get these ever increasing burps of gas coming out. So this was a really intuitive but very important to show clearly with the data that this would be a controlling factor. And if we look here at these superficial aerial surveys, so we measure lots of points on the ground, and they're represented by the two pink lines on the upper graphs, the two survey measurements. On a day where there was a low pressure system, we saw a lot of gas at the ground surface. And when we went back a few days later on a high pressure system, you could almost see zero gas. And so this really, you can imagine, is going to help us think about how we want to monitor and detect for gas at leaky wells or suspected leaky wells, because of course, this needs to be taken into account, and superficial methods is typically what's used. So we carried on and did a deeper confined aquifer experiment. So this was kind of the big experiment where we wanted to go a bit deeper, inject gas deeper into a more complex system and see what happened, track the gas and figure out the migration patterns, impacts, and fate. You can see here, this is a drone image of the site from above. You can see lots of little monitoring wells in the middle there, and they've got the experimental control tent and trailer there, and lots of different instrumentation. Conceptual model of how this looked. So remember I talked about this upper layer of diamictic, clay-dominated diamict, and below that we have these glacial outwash deposits with some sort of more coarse and medium sands. And so this is how our experiment looked conceptually, where we had lots of multi-level groundwater monitoring wells, we had superficial monitoring, and so on and so forth. And of course, lots of work to get this set up, lots of sonic drilling to get the monitoring wells and the injection well in. You can see some of the geology there. There's the diamictic clay, and there's some of the sands which it overlies, and some geophysics going on. And so there we had lots of interdisciplinary monitoring, and then we went ahead and injected 100 meters of a synthetic Monty gas over 75 days. So we made it similar to what the Monty gas would be like in terms of its composition of C1 to 3. And the gas was controlled by a mass flow control system, and down it went into the ground at 26 meters depth. And there we monitored it. So what happened? So I think this is a plan view of the groundwater monitoring well network. And we can see here we had various, the red cross is where the gas was going into the ground, and around it we had lots of monitoring wells. So what we saw was there was minimal dissolution of the gas into groundwater, actually. So from these monitoring wells, we can see here these different panels, A, B, C, are in different depth slices through the subsurface there. So 12, 16, and 18 meters depth. And it was very complex, sporadic, and I almost want to say random, but of course it's not random. The laws of physics are not random, but we see a non-uniform development of methane concentrations appearing there with these shaded dots. And then we look at the geology there, trying to understand what was going on and how this looked. And we start to come up with a bit of a conceptual model, looking at the geology there, where we see the gas moving, the groundwater flowing, the free phase gas moving around, being shunted left and right against the gradient due to lower permeability silt lenses and getting trapped under these different low permeability layers. And so quite a complex system developing of this leakage with what seemed to be quite minimal dissolution in groundwater. The geophysics helped us track this a bit better, and what we saw there was quite big decreases increases in resistivity across the different lines that we had set up. So obviously as gas filled the pore space and displaced the water, we were getting a lot more resistance, and so the resistivity increased. And so we could see there was quite a lot of free phase gas being retained in the subsurface, and even after we stopped injecting there. But the gas found a way to the surface. So our other monitoring and tracking methods, so we looked at the soil gases, and we saw eventually methane in the soil, the shallow, very shallow unsaturated soils began to increase, and we could identify with the isotopes there that it was our gas we'd injected, and it started actually to degrade somewhat. So there was some microbial oxidation, and we saw at the surface that even though there was this low permeability layers, the gas did find its way through and start to emit to atmosphere. And you can see some heat maps there with gas being emitted at ground surface in plan view from the flux chambers. So some certainly emitted to atmosphere, and you can see here the dynamic flux chamber data at the top. So you see the picture there of all the flux chambers we had at site continuously monitoring over the experimental period, and we saw methane fluxes increasing. And our eddy covariance system there was picking the same similar signals up, and we could see gas emitting into the air and being blown off into the atmosphere. And now we've had time to think and look at all this data. We've started to calculate a bit of a mass balance here as one of the key questions is, well, how much how much of this gas we injected emitted to atmosphere? And by looking at what we saw in the chambers versus the eddy covariance tower, we start then to be able to look at total mass emitted versus that retained in the subsurface. And we could see 20% emitted and 80% retained. So very interesting. So how bad is integrity failure? Well, of course, what we saw here and hopefully demonstrated is very complex interrelated reactive transport processes. So we're still working on what the impacts were. It seems, though, that most of the gas was kept in the ground. And so in some ways you could argue maybe gas in the ground is better than the gas going in the air. But the jury might be out on that for now, but there's certainly a lot to be thought about there. Not all failures are equal. I mean, of course, the risk posed depends on the exact area and what the receptors are nearby, and we perhaps need to think about thresholds of concern and so on. And one thing what we did see was quite clear is that monitoring and detection, current practices are certainly going to be inadequate to pick up the complexity that we saw here. And so just going and looking at the ground surface with very simple instrumentation is not really going to tell you the detail that we had, we observed in this study. Okay, so just to summarize then, just kind of a whistle-stop tour of this field research program. So the three questions we wanted to address. So why does well integrity fail? Well, a true scientist's answer is it depends. So it's not simple. It's a complex combination of environmental, engineering, regulatory, and even geopolitical factors. They all interact, compound, and that is what really determines if a well suffers integrity failure. And so we're not going to find a silver bullet here to fix this, or what, or how to look and mitigate. It's very complex, and it really is going to depend regionally. So we need to think about that and try to keep improving our understanding. Where do wells suffer failure? Again, it really does depend. In British Columbia, Canada, there doesn't appear to be a high rate of failure, certainly compared to some other regions, but it's not pervasive, and there's certainly not pervasive impacts to groundwater. But really, if we're honest with ourselves, this is poorly constrained. We really, while the data we have indicates that there doesn't seem to be pervasive impacts, we really don't have enough data to strongly constrain that. And so there's certainly need for more work as we move into the future. How bad is failure? A key one here is, as I've just talked through with the controlled release experiment. Again, I'm going to cop out here. It really is going to depend. So many factors will determine the overall migration patterns and impacts and fate of a particular case of leakage. In British Columbia, and the site where we've now looked very closely and examined this, we saw that a large portion of the gas was retained in the ground. So in a way, as I say, this is good news for greenhouse gas emissions, but perhaps it infers greater risk on groundwater if it's present. And groundwater, good groundwater, is not always present where these oil and gas wells are. So if it's not there, it can't be impacted. So maybe in those cases, if it's retained in the ground, it's better than it going into the air. And again, the longer term cumulative effects are yet to be constrained. So I think what you're getting from this, hopefully, is that well integrity failure is very nuanced, highly nuanced, and we need to understand it better to manage it and mitigate it. And it's certainly not a binary issue where it's either, is it good or is it bad? There's a sliding scale, and it's just not that simple. So quick couple of thoughts on monitoring of well integrity. So hope you've seen here that through some of the work we've done at Erie, that there's lots of different methods, multi-scale methods and technologies, and we're going to need these actually to constrain well integrity failure. We need standardized and methods and routine programs. So this is something that doesn't happen currently. We get these research projects which go out and look, but it's not routine that particularly plugged and abandoned wells, for example, or decommissioned wells are inspected. And really, it's going to take quite some effort to constrain the integrity status. And at the minute, we're not putting that effort in. And in the future, as we move into net zero, I would argue perhaps we need to do that. So there's this strong need to prioritize stewardship. And certainly not all wells are equal. And some might have a higher chance of failure than others. So we need to think about that. And little graph here at the bottom shows where we look globally at where people continue to monitor or have a post-abandonment monitoring program for oil and gas wells. Very, very few places, almost nowhere except Canada has a bit of additional monitoring post-abandonment, but all the other main producers, it's not clear if there's any guidance on post-abandonment monitoring, which kind of highlights that we really don't know what's going on after abandonment, and there's this strong need for post-abandonment monitoring. So final thoughts then on well integrity and net zero. So current integrity, I would say, we're getting more data and we're constraining it more, but it's still poorly constrained globally overall. Like, what is the status of integrity and how will that develop into the future? So we need to really think about constraining that as we move into net zero. More than that, long-term integrity is of course a bigger unknown and even less constrained. What will these wells look like in 100, 200, 1,000 years? We don't know that yet, and we can only imagine that they probably won't get better with age, quite like ourselves, unfortunately. Failure at scale, certainly, in my view, is going to pose a risk to net zero. If we get a large proportion of these decommissioned wells in the future having failure, that certainly will have some impact on net zero, and it's going to potentially cause a headache. Integrity is certainly difficult to predict. It's challenging to detect, hard to understand, but really we we should try to constrain it as best we can as we venture into net zero. And the positive on that is we certainly have the tools and the knowledge to manage and constrain it, but we at the minute we perhaps haven't had the focus. So stewardship of this legacy infrastructure as we move forward is going to be really important, and perhaps we can start to think about that more as we now move into net zero. Much work to be done, and hopefully some of the work I presented today contributes to our understanding on that. So big shout out to the students who did all the really, really hard work here and put in all the hard graft. They did a fantastic job. A big shout out to all of the multidisciplinary team. And as I mentioned, this really had to be a multidisciplinary research team to work on this. Big shout out to Roger Becky, who's the co-director of all this alongside myself, and all the other professors and investigators who covered everything from geology right the way through to atmospheric sciences, which was what really made this work well as it has so far. So there's some acknowledgements to all the funders down the bottom there, and some references I mentioned in case anyone wants to find those. And there I'll stop, say thank you very much for everyone's attention, and be ready to take any questions. Thank you very much.
Thank you very much. I learned a lot. It was quite a nice talk and lecture about the challenging issue of making sure leakage is not taking place in wells. I'm not sure, Aaron, can you, you just unshared your screen. Can you see us now?
Yeah, there you are.
Okay, fantastic. So I'll just give the floor to Sebastian to pick so many of these questions already posted. I believe more will come as well. So
yes, thank you also from my side, Aaron, for a really interesting, really great talk. I've seen bits and bobs, obviously, at internal seminars, webinars in pre-COVID times. It's great to see the full story and the evolving story. I'm going to try to group the questions sort of roughly in 3 areas. One is around leakage mechanism, one is how we can do the monitoring, and the third one is what does it mean for other subsurface energy applications. You have talked about how you use the Bayesian interference, about how you try to identify the key leakage mechanism, but there's still some number of questions where listeners asked you to please clarify. So the first one is from Kunal, and he wonders if some of the leakage is related to the lack of estimation of the dynamic stress field when the wells were drilled. Is there any evidence for that?
Yeah, I mean, there's obviously there's anecdotal. I mean, this is what's really interesting. If you talk to industry folk as well, who really know what they drilled the wells, right? And they often say, I've heard about rate of penetration has been suggested that when people are trying to drill very fast, so that's where we get these boom and bust times where, you know, there's these kind of gold rushes. And I think they saw that perhaps in the early 2000s with shale gas development. There was a lot of wells drilled very rapidly. And so I was suggested by some industry colleagues to look at rate of penetration. And what they had in Canada was there was lots of small operators. So this is where we don't get, like in the North Sea, you perhaps have because it's very expensive to do offshore drilling, fewer operators doing a much better job, can I say? But in the onshore development, there was lots of different small outfits drilling. They were drilling fast, get the job done, get paid. So there was these were anecdotal points. But the trouble is there data in a correct format to statistically test that? And some of these factors there isn't. While it actually took a long time for Elise to compile the database, it wasn't ready. It took at least probably 6 or 8 months to collect the different data sets into one usable data set, which could be then applied. The statistics could be applied to the Bayesian inference. So things like rate of penetration, even though it was a really interesting hypothesis, there wasn't actually readily or easily available data at scale for all 24,000 wells. You'd have to go into each well record, and there just wasn't scope. So I can imagine as we move forward, and I've got a student starting with me soon, we're going to try maybe to digitize more of the data, and then maybe try to test more of such hypotheses or ideas, looking at drilling methods, rates of penetration, other maybe downhole data that isn't in the right format yet.
It's really interesting. I'm going to sort of sneak in a little question here. So you talked BC and Canada as a case study. do you have any feeling, any inclination in other big oil and gas region where a lot of onshore activities are happening, be it in the Middle East, Saudi Arabia, Kuwait, UAE, be it in Russia, Kazakhstan? How severe is leakage there? Is there any data available, or is that something it's much close because there's perhaps less research? It's much more secretive. Not secretive is the wrong word, but there's much less information available, and it's even more difficult to get a handle on possible leakage risk compared to what you've done in Canada.
Yeah, you've answered for me, Sebastian. That you're absolutely right. No, I mean but that's really interesting, isn't it? Because we tried in some recent work related to all this, we tried to look at that global context. And you're right, that's very difficult to get the information. I had a Russian colleague try to look on, in Russian records, because I can't, it's difficult to navigate the websites and so on. And a colleague from the Middle East tried to look there. It's definitely not as well reported or easily accessible at all. So that's something I'd be very, and I know some other colleagues looking at this as well. The golden prize. What is the global situation? Can you compile? It's actually difficult to even say how many wells there are in the world, let alone how many had suffered an issue, or how many are abandoned versus active. So I could imagine in the future in net zero, wouldn't it make sense to have a bit more of a central body to know where this infrastructure is and the status of it, and to try and understand that? But will that ever happen? Will people want to cooperate at that level? I think there's obviously a lot of politics, with energy resources. And so I can imagine some places who are huge producers, you may never get that data. But from a global perspective, of course, it's probably important to all of us, isn't it? How many of everyone else's wells are leaking? It's not just affecting them. So,
thank you, Aaron. Coming back to sort of the actual process that cause leakage, and I can probably guess what your answer is going to be, but Saif asked, have you looked into the impact of drilling losses and cement quality on failure in your long list in your huge data set?
Not explicitly yet, but again, as you say, that's on the list. If we can get the data in the right format, we can start looking. So I think these are great comments. If anyone wants to contact me afterwards with ideas of other attributes or characteristics, I think the more we can get, the more we can perhaps nail down this combination of factors or maybe key factors which do tend to lead to issues with integrity. But not yet, but they're two great ones.
And Christine, so the last actual leakage mechanism question is, you show that one of the frequent failures were related to casing of the wells. What are the typical mitigation procedures for such wells? So
the mitigation wise, I think, obviously very well established in industry to repair these issues. This really isn't, rocket science in a way. It's quite standard that you can have an issue and you repair it. You can have cement squeezers, perforate the casing, put more cement behind it. I believe obviously industry are very good at actually locating leaks at what depth you're getting a leakage, or actually even diagnosing the leakage. If they need to, they can find it and it can be fixed. I think one of the things we've started to see though, which maybe is helpful but not so helpful, is once you have failure issues, it is difficult to fix. And it seems that it's more likely that a well which is already repaired or had to have remedial actions on it does seem to be found to leak later on. So although that might not be too sort of rocket science or it's quite intuitive, but maybe then at least we can then say wells which have had issues during their active life should perhaps be prioritized for more monitoring or additional monitoring in their inactive life, because they're the ones which might have more issues with leakage. But there's lots of remedial options. And I'm learning more about that. I'm not a petroleum engineer, so I've been working with my colleagues in IGE with Sebastian and learning a lot about that myself.
I think not myself. There are others who actually on the webinar who Morteza is actually asking questions. We come to Morteza in a moment. Coming to the monitoring side, Wilhelmine asked the question, thank you for the nice presentation. Is there a live monitoring scheme for all these many millions of wells in place to make sure any failure is timely detected? Maybe we just talked about data isn't really easily accessible in some of the big oil producing nations. But if you look perhaps more closely to home, your old home, Canada, what is done beyond the R&D type work that you have done to monitor? Is there something being actively monitored in Canada?
Yeah, well, as I think these research projects were a big effort along those lines, and so yeah, but that really is a bit of a lack at the minute. There isn't regular or standardized monitoring, and that's something, obviously I would argue for. I think there's spot measurements. I know, like, the regulator in BC is very proactive. They've gone out and done some aerial surveys with planes and on the ground surveys. But I think overall, globally, there really is not quite the level of post-abandonment monitoring that we need. And as I say, I'm completely biased from me, but that really is going to be needed to kind of prove that you've abandoned it properly, say 5 years after the fact. I think at the minute, a lot of places, they do after the plug and abandonment, they do a pressure test very shortly after that for a couple of hours. And if that's good, then they walk away almost in perpetuity. And it's almost then by luck, if someone goes back out, there can be triggers where they have to re-inspect a site, then they might find leakage. But yeah, I think moving into the future, I think there needs to be, particularly with the use of maybe new subsurface technology. So if you think about carbon storage in these regions, we might want to have a much better handle on the wells in the area and their integrity, because they could compromise that technology. So I think in the future, this isn't going to go away. We need to, and rather than kind of bury our heads, if we can manage it and learn about it, we'll be in good shape for it.
Thank you. And Yusuf, you gave a segue into some really nice segue there for the next set of questions. I'm going to start one from Alex. It's a two-part question, and I think it's a really intriguing question. And he says, thank you for the great talk. Can we integrate the sampling of some wells with modeling so to predict potential failures of other wells? If so, what parameters are crucial to predict failure or leakage? In other words, how can you model this process to predict the chance of failure and help sampling the right wells at the right time? Because you want to spend your sampling strategy where probably in areas where leakage risks are highest, and sample less frequently in other areas.
Yeah, absolutely. Yeah, and I think some of this work is maybe going to start helping contribute. That will be looking at next steps as well. Is, like I said, if you can pick out these risk factors, and instead of worrying about all, for example, 24,000 wells in BC, maybe we can narrow that down to a few thousand which are really at a higher risk, and then we can prioritize the monitoring to those. Because of course, it's completely unrealistic for me to say we need to monitor every well every year, for example. I mean, there's just not the resources, or it's just not feasible. So I think, yeah, modeling, a combination of field and monitoring to inform the field work can inform the modeling, and then we can maybe optimize the modeling, optimization, and so on and so forth. Yeah, I think this is where we want to go towards, because it's certainly not helpful for researchers or scientists to say we need to monitor everything all the time. That's not going to work. So let's try to sort of streamline that. And as the question said, that could be done, and hopefully we can work towards that in the coming years.
Doesn't make for the most exciting master's projects if you just go and monitor another set of wells for your MSc thesis.
Exactly.
You talked about CO2 storage and other geoenergy applications. There's sort of some questions, very similar questions. So, and I'm bringing up two here. So one is from, again, Kunal. It says, oh, that's the wrong one. Sorry. This was the one. What future impacts can well integrity failure have on proposed CCS projects, also green hydrogen storage? And Wilhelmine is a very similar question. How would this research help us to make sure we prevent leakage from hydrogen storage or CO2 storage in abandoned wells? Do you have any comments on that?
Yeah, absolutely. Just reiterate what I said before. I think actually there's more of a drive to understand this because of those technologies than for the sake of integrity failure itself, if that makes sense. I think these technologies and their implementation is really driving more thought on this. And I know for example, in Michigan, I know there's been a lot of work done on risk maps for CCS there, where they've looked at abandoned wells, I mean, that's obviously recognized as one of the key potential conduits for leakage or compromise of carbon storage sites. And so, yeah, this all feeds into that, because of course, you know, again, not all wells are equal. And so we don't want to just think about legacy wells as that they're in the area, so we can't do carbon storage there. We want to think about them in terms of what the legacy wells look like and what risk they might have of having integrity failure. So absolutely, if anything, those technologies will drive the research in this, I think, moving forwards, rather than just looking at it for the sake of looking at these. So yeah, let's see, but they're going to have to be considered, and hopefully with careful management and so on. I think it doesn't need to be a problem.
Thank you. I'm going to take one last question. There's still plenty of questions out there, and apologies that we can't go and answer all questions. There's some very specific questions about depth of the leakage experiment. They're probably in the papers, but because you talked about your collaborator Mortese, and he asked the question. Thank you, Aaron. What do you think about the role of the regulators? Can you please explain what are the guidelines for remediating well integrity issues for live wells and suspended wells in that region? Because the regulator will play a really critical role in making sure that we minimize leakage risks.
Absolutely. So yes, a good question. I mean, of course, industry and operators are going to do what they're required by the regulations. So of course, we know that then drives what's going to happen. I think in this region, in British Columbia, the regulator has been very proactive and been working with us collaboratively on this research. So that's been really, really powerful. In fact, I would argue it's difficult to do this research without collaboration with the regulator and industry. So I think that's where perhaps some of the earlier research on this issue got a bit stuck or limited, because if you try to do this alone, you don't know the details of the region and the nuances of the development there. So I think it's absolutely critical to work with the regulator and to advance this. In terms of I mean, every region's different. In this region of British Columbia, the regulations there are that during active life of the wells, there can be small integrity failures, so you can have casing vent flow, and it doesn't need to be fixed until the well is plugged and abandoned. So there can be an issue, but no matter what happens, when the well is plugged and abandoned, it must be fixed. So that in this region, that's the regulations there. And at abandonment, they must fix any integrity issues in order to move to the next stage and get what is called a certificate of restoration for that site. So I think you have to assume if a well is classed as plugged and abandoned, it should have no issues. It could have had issues during its active life, but they will have had to have been fixed if it's got a certificate of restoration. So that gives you an idea. But then the challenge is, though, there's nothing done after that currently. And that's not just in this region, that's globally. We don't go back 5 years later or 10 years later. We just say, it was good then, we just kind of walk away. And I think, unfortunately, even though it costs money and there's no money to be made at this stage, I would argue that probably we do need to go back in a managed approach to look at some of the wells which might be higher risk and check the integrity conformance is still there.
Okay. Aaron, thank you very much for a great talk.
Sebastian, it's hard for me not to ask any question. If you may allow, please. One quick one, please.
As so the co-host, nice. I'm going to allow you one final question because you need.
Yeah, Aaron, who owns this problem? I mean, if you detect a well is in trouble, is it a government problem, the company who did this decommissioning, the city hall? Who is actually?
Well, that's a fantastic question, Hadi. So again, it depends regionally, doesn't it? So different regions will have slightly different regulations. In British Columbia, the company is liable in perpetuity. So whoever was the operator or the owner of the well, and in some cases, actually, companies inherit wells that they didn't drill, which have a problem. And so if they bought out a smaller company, they will then own that well, and my understanding is that they're liable in perpetuity. Now, that's not the case in every region. So for example, I mean, in some cases you get orphan wells, right? So that's where maybe the company doesn't exist anymore. They faded away. And in that case, that's why in Canada, in Western Canada, sedimentary basin, there is a very big orphan well association, and they're looking at this because then it's the taxpayer who's dealing with this. And so that drives as well some of the research and innovation, because they want to make sure that's being dealt with as cheaply and as efficiently as possible. But yeah, that's a great question. Who does? And I know companies, do you think they want, is it fair even to be liable in perpetuity? There's an argument to say that's a bit unfair to be always liable for ad infinitum, right? So I know companies want to be able to have a point where they say, we're done, now it's the state's problem. But this is these policy and regulations, these are very, very complex and interesting. I think that'll be interesting to see how that plays out in the future as well.
Thanks a lot. I learned a lot this week webinar, like many others as well. But thank you very much for patiently answering all our questions.
Thank you to the audience for great questions as well. Thank you.
Yeah, of course.
Hadi.
The next week's speaker is Professor Shima Parsa from Rochester Institute of Technology in US. And Shima will present a talk on polymer-enhanced oil recovery. So until next week, 24th of June, 2021, 4 p.m. Central European, 3 p.m. British, 7 a.m. California, 9 Texas, and wherever you live, we hope we see you more and more in this channel. Stay happy and healthy, and also tuned into our channel. Thanks a lot, Aaron. It was a great talk.
My pleasure.
Thank you. Thank you, everyone. Bye-bye. Bye-bye.
Bye, everybody.